Please. Okay, so thank you so much for the invitation to speak. It's been great. And I would really like to genuinely invite you to find new applications of this technique of lip-sync decomposition. So that over there is from a different talk, slide I made, that it's supposed to be like a measure on a cat-zero cube complex, but it's also like a nighttime story. Okay, so we are going to see definitions and examples, and then from there, we're going to go to walled spaces. And we'll very quickly talk about applied examples, which is really also an invitation for you to explore that. And then we'll talk about the roller compactification, and together with the boundary. Finally, I'll introduce the lifting decomposition, and then I'll talk about 3 examples of uses of the lifting decomposition. So it's kind of a bit of a tour of a bunch of different theorems, okay? So definitions and examples. What is a cat-zero cube complex? I'm going to take a bunch of unit cubes. I'm going to glue them together isometrically along their same dimensional edges. There's my little glue. And I'm going to do it in such a way that I avoid positive curvature. So here I see, oops, that's not mine. So here I have positive curvature. So I annul that positive curvature by completing that 3 cube by adding that back vertex, and now that is non-positively curved. So examples of cat-zero cube complexes, they can be very wild. I won't insist that they're locally compact. So you just apply this construction and you can just do whatever you want. Here, I've more or less just randomly drawn something. So a specific type of space that you might be familiar with is the universal cover of a solidity complex associated to a rag, but there's really many, many more. And then on the level of groups, there's also many examples, and I will just point out to you that the isometry group, or I'll remind you that the isometry group of the hyperbolic plane is PSL bar, and the isometry group of the hyperbolic 3 space is PSL2C, because we're going to see that a little bit later. And also the category of cat-zero cube complexes and groups acting nicely on them is closed under direct products, which we'll also come back to later. So walled spaces. What are we going to do? We're going to take a set with a partition, with a bunch of 2-sided partitions, and those are going to be like the walls. And I will say it is a discrete walled space if it has, I will construct a discrete walled space from this data by taking the equivalence relation, where 2 points are equivalent if they belong to the same region. Then I will connect them by an edge if they differ by a single partition. And then in order to get this discreteness of this walled space, I require that between any 2 partitions, I have finitely many other partitions. If you don't have that, then you can try to put a measure on these partitions, and then that would give you a measured wall space. So this is like with respect to the counting measure. So here is an example. I have every region I'm drawing is non-empty. So I have north, south, east, west. And I guess west starts with a W, but not in French. So and so associated to these partitions, I get a square. That's cat-zero. It's non-positively curved. Over here, I do not get something that is non-positively curved since I have a 6 cycle. Over here, I get 4 squares, or rather the 1 skeleton associated to these 3 squares. And finally, down here, this is a bit of a combination of, say, this example and this example. But here, I again see that I have this corner of a 3 cube without having that back corner. So this is the construction for having a discrete walled space. So next, from this discrete walled space data, I'm going to construct a canonical cat-zero cube complex. And we're just going to fill in all of the cubes that are sort of missing. So since this one was already a cat-zero cube complex, it stays the same. However, this one, as you may recall, was the 6 cycle. And so now I'm going to fill in the front cube and the back cube, and then this like 6 cycle will uniquely determine this 3 cube. Again, this example was already cat 0, so nothing happens. And then finally, this one was similar to that first page. I just have 1 vertex missing and I added it. And if you have questions, please let me know. Okay, so it's a fact that this process is reversible. I can look at the equivalence relation that is generated by edges that are parallel along a square. And then I can cut my cat 0 cube complex, rather the vertex set, into 2 pieces by considering the complement along those that parallelism class of edges. And so this example here, I have 1 partition corresponding to the left and the right side of that. Another one here, another one here, here. That's 5 walls or 2-sided partitions. And then similarly over here, we have a higher dimensional example where we still have 5 walls. So if I have a cat 0 cube complex, I can cut along this way, I get 2-sided partitions, okay? So I also have a wall space. So the main character in this story is going to be the half spaces. And so the half spaces will be the sides of these partitions. And I will use this mathfrak H to denote the collection of these partitions, of these half spaces. And I call them half spaces. So a theorem, which is due to many people in different sort of slices, says that if you have a collection of 2-sided partitions associated to that via the walled space structure, we have a canonical cat 0 cube complex. Furthermore, if I start with a cat 0 cube complex and I perform this partition construction, then I have, again, the same cat 0 cube complex. Okay, so if I already started with a cat 0 cube complex, I didn't go anywhere. And this kind of canonical structure, if you will, is going to come up again in the lifting decomposition. So to summarize, cat 0 cube complexes are pretty easy to construct from these partitions. So there are abstractions for acting on cat 0 cube complexes, but I hope I have convinced you that it's somewhat easy to cook up, okay? So for the applied examples, we have 2 articles here. And if anybody would like my slides after, I'm happy to email them to you. So they're both along the lines of robotic movement, configuration spaces for robots in some sort of environment. This one is about a robot. I think you can't. So this is a configuration space for a robot arm that has length 6 in a width in a tunnel of width 2, and you will also see in this paper a comment, or rather a part about Black Lives Matter, because around the time that the author and his collaborators were finishing this project, there was a robot that was used for the first time to execute somebody without due process in the United States. And so as we talk about applications, this is VECTA after all, I think it's important to also consider the ethics behind the possible applications and the work that we do. So similarly over here, we have another one. Again, I invite you to explore these 2 articles. So what is the roller compactification and the roller boundary? So I'm going to consider most of the time my cat 0 cube complex to be the vertex set. If I start talking about the cat 0 metric, then I will be filling in those cubes, but for most of the time, it's going to be just this discrete set. I'm going to take a vertex and I'm going to associate to it all of the half spaces that contain it. And because of the abstract part that I was discussing earlier, this is going to separate points. Namely, 2 vertices will always be separated by at least 1 partition. And so we get an isometric embedding in this form from the vertex set of the cat zero cube complex to the power set 2 to the h. I'm going to topologize this via the standard cylinder sets. And if you're familiar with that, then now you know. If you don't, then don't worry about it, okay? So here, the symmetric difference between those two sets is this Venn diagram. So I take one minus the other, union the other minus the one. What is the roller compactification? With respect to this topology, this is a compact space. I have managed to find an injection into that compact space, and therefore I can just close it in the image, and then that gives me the roller compactification, and I can also remove the image of that map, and that gives me the roller boundary. It's important to note that both are totally disconnected, as they are a subset of a totally disconnected space. And it is possible that the boundary may not be closed. It won't be closed when essentially the space is not locally compact. So what are nice examples of cat zero cube complexes are trees. And the Gromov boundary of the tree will be the same as this roller boundary, provided that the tree is locally compact. If it's not locally compact, the topology will be different, but as sets, it will be the same. The very nice, or possibly not nice, depending on how you look at it, structure that the roller compactification has is that the product of the compactifications is the compactification of the product. Since Z is a tree and we know what its compactification is, we just take positive and negative infinity, then the compactification of the product is this sort of infinite square, okay? In this infinite square, we have these corners that correspond to the product of the boundaries, and those are going to be, those are important in this theory. And then we also see that we have these flats at infinity corresponding to the possibility of taking the boundary of one factor across the space in the other factor. So we do have these flats at infinity. Okay, so question, how do you know when a set, so I'm thinking of 2 to the h as subset of h, the half spaces. How do I know when a collection of half spaces actually belongs to the roller compactification? And the answer is that it should have 2 properties. It should be a consistent and then separately a maximal set. Consistency is going to be the second star of the show in the context of these half spaces. What does it mean to be consistent? It means that if I, if I choose a half space, then I do not choose its complement. Here, H star is the complement and X bar of H. And then separately, if I choose a half space H, and then I have a larger half space K, then I must also choose that half space K. Maximality just says that I have chosen one of the 2 sides between H and H star. So one of the things that you should, and then H versus H star is not a preferred direction between H and H star, it's just a name. H double star is the same as H. So a remark is that if I have an arbitrary subset in the in X bar, then the collection of half spaces that contain it is automatically a consistent set. That's somewhat obvious from the point of view of the second condition. And if you think about it for a second, the first condition is also immediate as well. So the spoiler here is that the collection of consistent half spaces will exactly correspond to will exactly correspond to collections that contain a set. And if you do it sort of twice, then you will get a closed convex subset of the roller compactification. So that is where we're headed with the lifting decomposition. And I think I'm stopping at 340, right? Okay. So basic 350. Okay, that's the basic examples of consistent sets. Well, I can look at the interval between 2 points, and that's going to be the intersection of the half spaces that contain both of them. So in this infinite interval example, I mean, it is itself an infinite interval, but let me not worry about that right now. If these are my 2 points, then everything sort of shaded in here is the interval between them. You can, I think, easily convince yourself that it is the intersection of the half spaces that contain both. A more exotic example is, again, just something I randomly drew. And here I have a finite interval where I have taken these 2 points and I'm intersecting all of the half spaces that contain them. And if you just play around with this, it will be evident that they are, that this is the interval. So a fact is that cat0 cube complexes are nice because they have 3 nice metrics. The L-infinity metric, it makes it into an injective metric space, which tells you that closed balls are Helly. The L2 metric makes it a cat0 space, which means that geodesic triangles are no wider than those from the Euclidean plane. And this has important consequences of contractibility and unique geodesicity. But my favorite metric is the L1 metric because it has the property of being a median space, and the actual X has the property that it's a median space. And this median property does extend to the roller compactification, which is also why I like it so much. That gives it a median algebra structure, which is amazing from my point of view. So what is the, that's my little heart there, okay. What is the median in this case? It's this Venn flower, if you will. You take the 3 sets and you take their pairwise intersections and you take the union. That will give you a canonical point in the compactification. It's something to check. And it has all sorts of nice properties. And again, if there's any questions, please let me know. So one of the things that we can do with the cat0 cube complex is we can take projections in them by forgetting some of the partitions that we had. So here, I'm going to take a subcollection of my half spaces, and I'm going to insist that it's closed under its opposite. So if I take one half space, I'm also throwing the opposite into B. B is supposed to be for bad, or the things that I'm throwing away. And I'm going to just consider the, I'm just going to forget that I had those partitions. I do the same construction. I get a walled space. I complete it to the cube complex. Then I take the compactification and I get this projection from X bar to the associated cat0 cube complex to this collection of H minus B. Right, and what is that projection? Well, it arises on the level of the subsets, and I just take my set S and I just remove whatever was in B, okay? So I always have this projection. As an example, we have the median. You can project any point to the interval. This will give you the median. And this is an example of such a projection. What you are forgetting are the half spaces that were containing both X and Y. So one of the reasons that the projection is very nice is because it's equivariant under the median map, which is what I mean by this equation. And so a question you can ask is, when can you reverse this projection? When can you find a map backwards? And if you can find a map backwards, is it canonical or not? So the first example will show us that it is not always possible to come back. And that is just pretty evident. If I forget these 2 edges, then I get a collapsing of these 2 edges to have a common vertex over here, and I just can't come backwards. On the other hand, if I take my bad set to be all of the half spaces, and I forget all of those, then the associated cat0 cube complex to no partitions is 1 point. And clearly I have the number of points in my compactification as a way to come back. So if it does exist, it may not be unique. So the point of the listing decomposition is going to be a section to this projection that is unique. So proposition, if S is consistent, I'll remind you being consistent and maximal corresponded to being a point, and now I'm just insisting that it's consistent, possibly also could be a point. And this again means that if I choose H, I don't choose its opposite. If I choose H and there's a larger half space, then I must also choose that larger half space. In this situation, I can look at the projection from the original cat-zero cube complex to the associated cat-zero cube complex, where I throw away the consistent set and its opposite, and its opposites rather. And I will have a section, and furthermore, the image of that section will be the intersection of all of the half spaces that were in my original consistent set. I include further references here because the content of what we did was to somewhat uniformize some other examples that were available already in the literature and make this general framework for that. I'm going to prove for you that if I have a consistent set, then the mutual intersection of those half spaces is not empty. The first step is just a standard analysis of the 5 possible configurations half spaces can have. And I'm going to just show you the next picture and move on. So the fact that I have these basic 5 configurations means that whenever I check to the intersection pattern of 2 half spaces, I just have to check these 5 conditions. Any 2 half spaces will always be one of these 5 types. So consistency tells me that pairwise intersections are non-trivial. The second step is that the Helly property for the half spaces says that if I have pairwise intersections being non-empty, then finite intersections are non-empty. And then finally, because I am in a compact space, the finite intersection property allows me to go from finite intersections to complete intersections. So there we go, pairs finite total. Oh, I guess there was supposed to be an H there that didn't survive some edits I did. Okay, so what are some other steps in this proof? Yes.
I'm a bit confused by the statement. So I thought that in this projection you were removing the half spaces in F.
Yeah.
But then when you go back, so you only have the things you removed.
So here I made a choice of things that were, say, bad that I removed. Okay. The choice of things that I am removing here are the consistent set and its opposite. Did I answer your question?
Okay, but then you're saying that the image is of this sigma F.
So I'm saying there is I'm saying I can go back.
Okay.
And the thing that I come back to is the intersection of all the half spaces that were in the consistent set.
Okay.
Is that better?
I'm still confused, but
okay. So maybe just very quickly, if I were to, so here at infinity, let's say, I have a copy of D that is compactified. The half spaces that contain it are all of the right-facing ones. So there is a projection from this infinite square to the infinite compactified line, and I can reverse that by placing that there. Now you will see here, there's that infinite compactified line, there's this infinite compactified line, there's many infinite compactified lines, and I'm like, where do I put it? Well, I put it where the consistent set told me to put it. Okay?
Okay, thanks.
You're welcome. Thank you for the question. Okay, so other steps in this proof is I'm going to, well, first I showed that this intersection is not empty. And again, this is in the roller compactification. If I have an arbitrary set in 2 to the h that is consistent and maximal, and I remove the consistent set and its opposite, and then rejoin the consistent set, that will again be maximal and consistent. It's something you have to check. And then the fact that it's an isometry just is immediate, because if I start with these 2 sets, the distance between those 2 sets is the symmetric difference. And if I add my consistent set, then I'm going to remove it again when I look at the symmetric difference, and so I get the same cardinality. And then finally, the last step is to apply that Sageev roller duality to get the fact that the thing I have, the thing that I come back to, which is this intersection, is in fact the compactification of the associated cat-zero cube complex located in the correct spot, if you will. So actually your question was, came at the right moment. I think it's more clear now. Okay. Okay, so that's a sketch of this lifting decomposition. The main real parts are the pairwise intersection getting you all the way to infinite intersections via the finite intersection property and the Hellier property, as well as this canonical way for producing cat-zero cube complexes given some partitions. So what are some examples and uses? So Guralnik has an example of this, where he takes a cat-zero geodesic ray, and he considers the associated, let's say, deep half spaces, or T for transverse. And I was a little bit sloppy here with the definition. It just means that you can take an arbitrary neighborhood of your geodesic and then wait long enough, and that set will be inside of your half space. And so this is actually a consistent set. So let's have a look at this example. If I'm looking at the space the group Z cross F2 acting on its cubical Cayley graph, aka the universal cover of the cell-body complex, then here if I look at this cat-zero geodesic ray, which is T comma the identity, then it looks something like this. And as I act by the group, it is remaining parallel. So that is a direction that is invariant under the group. And so what I obtain is that the intersection in this case is the compactification of the free group or of the street at positive infinity. I could have also chosen negative infinity and I would get the other one. And so this will be a gamma invariant compactification, compactification of a cat-zero cube complex at infinity. And in this case, the action will be essential and non-elementary. The original action here was essential, but it was elementary because I had this, this direction that was invariant under the group. The essential core is important, and I'm, I guess, going to skip it. So Caprace and Sageev showed that if you had a non-elementary action, then you always had an essential core inside of your cat-zero cube complex. But we were able to say, if even your action is elementary, either you have a finite orbit in the roller compactification, or you have an essential core, which is possibly at infinity, and that's totally fine. You just look at this quotient and you move on, and it is essential and non-elementary. And this is an example of such a case. Okay, so that was the first application. Now the second application is going to be a little bit different in flavor, where we're going to be considering probability measures on the roller compactification. This is a construction of Monod and Shalom for trees, and then we did it for cat-zero cube complexes, finite dimensional. So I'm going to take a probability measure on this roller compactification, And I'm going to consider as my consistent set the collection of half spaces that contain at least strictly larger than 1/2 of the measure. It's pretty easy to see that this is a consistent set. And it is less easy to see, but not difficult, that the intersection of all of these half spaces will actually be an interval. So here are two examples. The associated interval to this average of Dirac masses is this little interval here. And then the one associated here in this plane is an infinite interval. So using this, we were able to show with Chatterji and Iozzi, and then also with an appendix by Caprace, that if you have a irreducible lattice in a product SL2K, where K is R or C, such as an irreducible lattice in the product of the hyperbolic plane with itself, or the isometry group of that with itself, or hyperbolic free space with itself, then every action on a cat0 finite dimensional cat0 cube complex, independent of whether it is locally compact or not, must have a fixed point. Okay, so this is in contrast to the reducible case, where the reducible co-compact lattices actually are cubulated, namely they admit geometric actions on cat0 cube complexes. So question, why am I talking about measures and then talking about this kind of rigidity type results? What is the connection? So I guess I'll just have time to talk about that connection and not talk about the third application, which is then an invitation to you. I can tell you more about that third application tomorrow. Okay, so the question is, what is the connection between this theorem and measures on the compactification? And the answer is indirectly about the Furstenberg-Poisson boundary. So what is the Furstenberg-Poisson boundary? I start with a probability measure on my group gamma, who generates gamma as a semigroup, or the support of it generates gamma as a semigroup. If that's not the case, you just pass to the subgroup that it generates, so that's not a real assumption. And the Furstenberg-Poisson boundary is, in some sense, the limits of the random blocks. So that space is an abstract measure space, and then we try to find models of it via some sort of geometry. That's like a loose sketch of a direction that you might want to go. So what are some key properties of the Furstenberg-Poisson boundary? Well, gamma acts on it, preserving the measure class. And the special measure that it comes with is actually stationary for the gamma action. And that just means that if I push forward the product of mu cross nu via the action map, gamma cross the action going to be, that push forward is going to be, again, nu. Alternatively, you can say that nu, rather than being invariant under gamma, it is on mu average invariance under gamma. Another interesting but also important property of this boundary is that it's dimmer amenable, which means that if I have an action by homeomorphism on a compact measureable space, as I do now, then there's a gamma equivariant measurable map from this Furstenberg-Poisson boundary to the probability measures. So that starts a super rigidity machine that was, I believe, established by Margulis and has been exploited in different circumstances via this technique. So I have come from the Furstenberg-Poisson boundary, and now I'm talking about probability measures on X bar. So what else do I know? If I have an irreducible lattice in a product of locally compact second countable groups, G1 cross G2, then there is a measure on gamma, so that its Furstenberg-Poisson boundary is in fact a product, and not just an abstract product, but a product of boundaries for these ambient locally compact second countable groups. in this context, also applying double ergodicity, we can deduce that the second bounded homology of gamma with some certain coefficients splits as a direct sum, that should be a direct sum, of the continuous second bounded homology of these ambient groups where the coefficient modules may have changed. And using this, we get a access to another superrigidity machine via the second bounded homology, which really arises from this decomposition of the second bounded homology. So whenever you see second bounded homology and superrigidity, this is why. And it's also why we are talking about the second bounded homology and not the 10th bounded homology. It's because of this double ergodicity of the boundary. And then finally, since X is totally disconnected, these GIs, I'm assuming, are having finitely many connected components. I get that the superrigidity tells me that this extends, and however, because it's totally disconnected and these groups are, let's say, connected, then I land in a connected component, it's identity. Okay, so what are some more theorems that you can extract from this? Well, you can have a T alternative. So if you have now gamma, this is the first time I'm assuming that it's actually a subgroup of the augmented group rather than just being a representation. Either it contains a freely acting free group, or it has an orbit of cardinality to the n, where n is at most the size of the dimension, at most the dimension of x. Another theorem that you can extract from this is, again, I'm choosing a generating probability measure on gamma, and I'm assuming that I have an arbitrary action on the cat-0 complex. I'm not assuming anything about the complex X except for finite dimension. I'm not assuming that that it's locally compact. I'm not assuming, okay, it's just finite dimension. Then there's a finite index subgroup and a gamma 0 equivariant measurable map from the first order Poisson boundary to the roller compactification. The existence of this finite index subgroup is directly related to this theorem because, for example, if I have an orbit of size 2, then I may have to place my Poisson boundary, crush it all to a point, and then I may have to place it on, one point versus the other. So I have to pass that finite index subgroup because I don't know if I should put it like on the left or the right, if you will. Yes, so I like this theorem a lot. It has not really any assumptions. And if you do not have a finite orbit, then you will have this freely acting free group and you will get a genuine measurable map from the first order Poisson boundary to the boundary of the roller compactification. And that will have lots more properties that are very nice. Yes. So maybe I will just quickly say that there is a special subcollection in the roller boundary called squeeze points that allow you to control cat-0 geodesics. And so with Le Coq and Mateus, we were able to show that in this time, I'm assuming that the action is essential and the complex is irreducible, so it's essential and non-rhometry, then we can get convergence of the random walk to the visual boundary. But we do this via an understanding of what is happening in the roller boundary and the fact that it's actually converging to these special points called squeeze points, which we can then directly compare to the visual boundary. So that's my time. Thank you so much.